Okay, so this is the second lecture of our course. Uh, we will uh, discuss about the property in materials. Okay, so some property in material science. I will start with the what we call the imperfections. So in materials, we imagine all solids or all materials like metals, ceramics, or anything that you can imagine is made of an atom. Okay, so you have the uh, atom arrangements. Okay, atom arrangements in every materials, but that arrangement is actually uh, it's not perfect. Okay, so we will start with the imperfection of material. So in material, okay, uh, we'll start with the imperfection in solids. Okay, so there's no perfect atomic order. Okay, or we call the ideal solids. There is no such materials exist today. Okay, so all materials contain large numbers of various defects, okay, or we call imperfections. Somehow this imperfection, okay, by controlling the amounts, okay, or the numbers of defects, uh, it can improve some characteristic in material. So imperfection does something to our material, and we if we can control that imperfection, we can also uh, control some characteristic that can be observed in materials. Okay, so there are two. Okay, in this section I will show you. Okay, we call the first one a point defect, and the second one is linear defect. So let's start with point defect. Okay, so point defect. Okay, so we start with this arrangement. Okay, so here's the atomic arrangement of materials. Okay, so you see here there are two conditions. Okay, the first is vacancy, where there is no atom here. So it should be an atom here, but there's not. Okay, we call this phenomenon its vacancy. Okay, and then we have self-interstitial, which is there are an atom. Okay, uh, the same atom inside here. Okay, among the other or the same atoms. Okay, so that's self-interstitial and vacancy. And we also have what we call impurity. So this is all point defect. So the defect is only affected in like a dot. Okay, like a dot here. And we have also another thing called impurity. Impurity is another atom. Okay, another atom. So you see here the blue one. So imagine that's the materials atom, and this orange and the green one is another atom, so different atom. Okay, if it is smaller and it can fit between this blue one, we call this interstitial impurity. Okay, and if it is the size similar or almost the same size with the blue one, so the green one, we call that substitutional impurity. Okay, you can check the video. Okay, this is how the the alloying. Okay, so let's say one by one. Okay, so we can change the property of metals with the impurity. Okay, or non-metallic elements. Okay, like carbons or molybdenum, nickel. So the easiest way to understand the metals is through steels, okay, because it's the most used metals, okay, and this is some alloying elements that can be added into iron. Okay, it can enhance its property. It can make it stainless. It can make stronger. Okay, here's the design or schematic design for an atom arrangement. And imagine this is the alloying element. Okay, and that's what will happen. It will disrupt. Okay, it will disrupt the order. Okay, the large one it will disrupt, the small one also disrupt. Okay, because it will at least disrupt the bonding of the atoms. Okay, this is interstitial, this is the substitutional, and this is a smaller substitutional. I'm advising, or I'm giving you a suggestion to watch the whole video. Okay, so we go back to this slide. So now we go for a linear defects. A linear defect. Okay, so before is the point, and now it's a linear, meaning if we see this arrangement in two-dimensional design, there's there are missing line here. Okay, missing some atoms here. It's kind of like a line here, right? This we call this the linear defect, or we call in these terms, okay, in material science term, we call dislocation. So it can happen here, okay, and if the plane there's misalignment like this one, the right one, okay, we call this is the screw dislocation, okay, because it can act or behave like a screw. Okay, but I will not explain that further. I would only explain slightly for what dislocation means. Okay, so this is some simulations. Okay, so here's what the dislocation looks like. So here's the atoms, arrangement of the atoms. Okay, so imagine you have a force applied here, okay, and it will make this line or this dislocation moves, okay, because of these shearing forces. It's move slowly until it reach the end, okay, or in this case it's reaching the grain boundary, or the dislocation will catch up with the other dislocation. Yeah, this is the three-dimensional simulations. I hope you get the idea of the linear defect, okay, through this image. Okay, this this video, which is basically what dislocation means, how it looks like, how it's transformed. I'm suggesting you to watch it. Okay, I think the explanation quite short and quite understandable. Okay, so let's just skip this. So let's go back to go back here, and we will going for the second section, which is diffusion. So diffusion, okay, maybe you've heard before, okay. So this is a phenomenon of material transport by atomic motion. So here's the some mechanism here. You can imagine the vacancy diffusion, okay. So the atom move to other vacant space here, and it can also interstitial. So this is the smaller atom here, okay, and it can move, okay. This is some substitutional diffusion simulation. So it can move like this, okay. It's the simulation. Yeah, it's the simulation. We can try to watch it, okay. I think that it's quite easy to see the movement, okay. The other uh, the other section in diffusion is semiconducting material, because, okay, to produce the semiconducting material you need to have a diffusion phenomenon inside the the semiconducting materials, okay. So to fabricate the semiconductors you need to usually um, heat it the the impurity, and because it is in the higher temperature, usually it's gas, okay. We call this the procedure is called chemical vapor deposition. So the gas will deposit into the silicon wafer, which is the base material for semiconductors, okay. So the second step, the impurity will goes deeper, okay. So the temperature is heated once more, and then the impurity goes inside. So the impurity will affect the semiconductors, because it will affect the behavior, okay. So the property, or the electrical property will enhance significantly, okay. I will not go into detail about how the property is changing, but the idea is you need to have atomic movement, okay. You need to dope the uh, the impurity inside the silicon, okay, to change the bulk property, the bulk materials, okay. So we call that solid state diffusion, and this is the size of the IC chip, okay, the integrated circuit chip. And usually the processor in modern laptops is around 10 nanometers, or even 7 nanometers, and maybe in the future we will go below 5 nanometers, okay. So that's the sizing, and then uh, the impurity that we discussed before is called doping in semiconductors terms, okay. So doping, for example here, okay, what does it do? It can change the property, like I said before. So for example here, okay, the red one here is the phosphor, okay. So phosphor, uh, uh, it will goes inside the silicon here, and you see here the dot is adding one dot here. So see here is 8, and here it's 9, it's plus 1 here. So it changed the property into what we call the n-type semiconductor, which translate as the semiconductor has an electron here. So it's the, it's having more electron, okay? And for the boron here, it's white. It changed this one into white here, okay. So we call this phenomenon imagine the electron already excite, okay, or move to another place, and it leaves some vacancy. So that vacancy we call hole in semiconductor. So this is electron, this is hole. We call N and P in semiconductor. Okay, and N and P usually uh, fabricated simultaneously and then combined together. And yeah, depends on devices. So that's some brief information about semiconductors. As at least you get the idea how the semiconductors fabricate. Okay. Okay. Another topic is the phase diagram. Okay. This is also interesting because we have learned from elementary school that water, okay, this is water, water diagram. Water can have three phases. Okay? It can have solid, liquid, and gas. And if we observe closely, it has this triple point here. So this triple point, so this is pressure in the y-axis and then temperature in the x-axis. So if we change temperature and pressure, we can change the phase as we want, right? So that's water. But how about the other materials? So the other materials, especially solid, they also have this diagram, this kind of diagram. We call it a phase diagram. So phase is not only solid, it's not only liquid, it's not only gas. It can be different solid. So you can say solid A, solid B, solid C. If they have different arrangement of atoms, different growth rate for the grain, okay, you can say that it has different phase. Okay. So if we see here, okay, so this is I forget what this is. I think this is the strontium and tin. I think tin and strontium. So from here, okay, imagine this is the temperature, this is the composition, okay, composition of the element. Okay. So here is our point. It's in the higher temperature. So in the higher temperature, it says it's L. Usually L means liquid, so it's in liquid phase. Okay. And then cooling down slowly, okay, cooling down slowly, we go here in E. So we have L phase, we have alpha here. Okay, so from this line, okay, if this point crossing this line here, there are alpha growing. Okay, there is a nucleation. Okay, we call this nucleation. Okay, and then it starts to grow until it reaching its limit. Okay, we call this grain boundary. So this is grain. Okay, this is grain boundary, and this is already all alpha phase in this F point. Okay, and then we start cooling down one more time until G here, and then we have this little or small needle here. We call this phase beta phase. Okay, so this is alpha plus beta. So we can actually, from phase diagram, okay, we can control which phase we want to produce and how much. Okay, so how much alpha in compare with beta we need. Okay, which one is considered stronger, maybe, or maybe another property more ductile, more tough, if it is metal. Okay, so that's why the phase diagram is important, and this is video to illustrate how the phase or the arrangement of atoms can be observed. Okay, so what is grain boundary and microstructure? So imagine this is the atoms, the black one here, one atom. Okay, so I will make it a little bit fast here. So you put atom, arrange in some particular orders, and you will get a different arrangement. Okay, and because of different arrangement, it will create some line. Okay, that it is we call the boundary, the grain boundary, and this is the grain. So there are 4 grain. Okay, 4 grain here, 1 2 3 4. Okay, so it's 4 grain. And so we can only observe grain under microscope. Okay, and under the microscope. So that's the schematic representations. So we have imperfection, diffusion, phase diagram. All of these 3 nodes are related to each other. Okay, so as a summary, I will conclude. Okay, so we have a structure here, specific. Okay, composed of each composition. Okay, so in semiconductors, we have this composition. There are phenomenon here, diffusion. Okay, and that is how we fabricate the IC. Okay, we have alloying process here. We have solid solution concept. The different phase in one chemicals. Okay, in metals, for example, in alloy. And then from the solid solution, we have the solid solution strengthening from that alloy. Okay, we add impurity. It can alter the property. It can strengthen the materials. It can change the behavior. And then also in alloy, there are concept of dislocation. So maybe I missed this dislocation before. So dislocation, if you have dislocation in materials, okay, when you move that dislocation, okay, or when you push the material, gave the stress, shear force, okay, the dislocation will move. Okay, for example, to make it easier to understand, imagine a spoon. Okay, a stainless steel spoon. Okay, if you think the spoon, the atom arrangement of spoon is really perfect and crystal, like a crystal, when you pull the metals, okay, when you pull that spoon, it should be break, right? Easily break. I mean, if you are strong enough. Okay, but no, right? The spoon will bend. Yeah, the spoon will bend. So why it's happening? So that's because when you are deforming the metals, the dislocation moves, and that's when the materials deform plastically. Okay, so that's why the materials or the metals didn't broke at that point. Okay, it should be broken, but it is strengthening. It is strengthening because of the dislocation. Okay, so that's the concept of the material. We have the imperfection, we have the diffusion, we have the phase diagram. Okay, I hope these 3, at least you can understand brief, okay, brief slightly. So think this is for the second lecture. Hope you guys enjoy this recording. If you need anything to ask, you can email me or discuss in class, or email me if you cannot enter the class. Okay.